So how how well a metallic strain sensor is working, that is determined by a parameter called GF. GF is nothing but the gauge factor. Remember this gauge measuring? So gauge factor. How do you represent the gauge factor? Gauge factor is simply equal to delta R by R divided by delta L by L. What is delta R? If R is resistance, delta R is the changing resistance. So length, changing length by original length and changing resistance by original resistance. So it is also known as strain. This one. You can call it as the strain. Change in length. So we can write the gauge factor GF as equal to delta R by R divided by this is the gauge factor. Now, what type of metals are used? You cannot use any metal. There has to be certain set of metals which are used for strain, metallic strain sensor. In strain gauge. So what can you learn? It's based upon this gauge factor. So we got the gauge factor GF equal to change in resistance by R divided by the strain. Strain, we can call it strain. Strain. So this strain gauge you can use. It's got a shape here. Let me draw it in a well. This is how it looks like. This design, you can have any design based upon the situation. I'm just drawing it. You can have this one also. Shouldering. So this is the grid. And this is the foil. So the materials that can be used, the metals that can be used for metallic strain gauge, there are two types of materials. One is constantan and second one is called karma. Basically alloys. Constant is copper and nickel. So this is basically copper and nickel. And Gamma is basically nickel alloy plus chromium plus aluminium What is the concentration? This 55 is copper, and how much should be nickel? If it is 55, how much should be nickel? If it is 55, how much should be this? 100 minus 55, which should be 45. It's 74, right, 74 20 3 3 total 100. So these are the two alloys which are used to make metallic strain gages. By the way, what is the application of metallic strain gauge? Where can we use this sort of sensor? It's got different application. First application is in aerospace. Second application is in civil engineering. That is in medical. Aerospace means those aerospace parts, they are under harsh environmental conditions. So they are under severe strain. So one needs to test how will they perform. But what is the amount of strain that is happening? We need to detect that. For that case, we require metallic strain gauge. How much strain is happening? Suppose an aircraft is flying, it is under constant strain. So we need to measure it so that before the failure of the part, you can replace it. Okay. So in that case, you can use a metallic strain sensor. Civil engineering maybe in bridges. And dams. Suppose there is a small crack, you cannot see from the naked eye, but from the strain, you can find out that it is going on. Seismic attacks, the earthquake attacks. Sorry. Seismic attacks, earthquake. So basically, it's about early detection of any flaw in both these cases. As a medical diagnostic sensors में कहाँ पे use होता है? For example, a person is going dialysis, or you need to inject a fluid into a body. So basically, it's fluid pressure. Mainly is associated with fluid pressure. Whenever we are inserting a fluid, it can be anything. The body, the biological body undergoes some sort of strain. So, metallic strain gauge can detect that. Now the question is, we have understood that these two types of alloys are used for metallic strain sensor. और उसका जो gauge factor क्या है? There has to be a change in resistance due to some mechanical strain. So why these two? Why not any other copper? Because we need to understand that we can have only those materials whose resistance is stable. With respect to temperature. Okay. Because if you take any metal, for example copper, and if you increase the temperature, there will be vibrations, there will be phonons. Only current, there is one copper wire. This is a copper wire. It is a good conductor of electricity. So it is causing current to pass. Basically, electrons are moving in the opposite direction. So now, if you increase the temperature here, what will happen? There will be vibrations in the crystal lattice. By vibrations in the crystal lattice is called, there is one name associated with them, is called phonons. So it will hamper the conductivity or the resistance. So we cannot have such material for a metallic strain gauge, because then whenever there is a temperature change, it will affect its gauge factor. So we need to have such material where the resistance is stable. Resistance stable का मतलब है, with temperature का मतलब है इसका जो PCR है, PCR याद है? Previous class we have discussed PCR, temperature coefficient of resistance, when we were discussing RTD. Did you remember, I think? Okay, this is in RTD. Previous class we discussed here. So this is actually TCR. So it means how much the temperature, how much the resistance changes when we increase the temperature. So this has to be very low for materials used for metallic strain gauge. ऐसा alloy हमको लेना पड़ेगा क्योंकि TCR बहुत कम है. So that comes in the shape of a constant alloy. This is the composition, or thermal alloy. Now the question is why? Why do these alloys have a low TCR? Basically, we need to go, for the first case, we need to go deep into the phase diagram of CuNi. Simple sign. There's nothing complicated about it. So this is 1 1 0 0. This is 1 6 0. This is temperature in degree C. 0% nickel and L. This is alpha. इसमें क्या होगा? What should be inside this? This is L. This is alpha. What should be inside this region? This is L. This is in between alpha and L. So alpha plus L plus alpha. Good. Very good. L plus alpha. L means liquid. Okay. So this is where it is completely getting converted into liquid. So इसलिए मैं ये वाला जो region है, I will call this line as the liquidus. And tell me what should be this line called? This is liquidus. This line should be alpha is a solid. Alpha is a solid. Solidus. Solidus. Hello. This is quite a very simple phase diagram of copper and nickel. So basically, so it completely, the copper and the nickel, they completely form a solid solution. They mix 100%. So the copper and nickel mix food. So basically they are a solid solution. Or alloy, whatever. So in any solid solution, जो solute होता है, that comes in as a defect. So with a solid solution, it means that here implies that the solute is a defect to what? To the crystal lattice of the base material. So in this case, the solute is nickel. यहाँ पे solute क्या है? We are talking about the copper and a nickel mix. यहाँ पे solute is nickel and solvent is what? Copper. So as they have mixed 100%, there is a rule which is called so they have undergone saturation. They are mixed totally with each other. So copper and nickel. This is forming the alpha phase syntaxis. They are mixed in such a way that no further addition is possible. तो इसका मतलब क्या है? ये जो डिफेक्ट क्रिएशन जो हो रहा है due to the addition of the solute, there cannot be any more defect creation. ठीक है? So temperature बढ़ा के, when we are increasing the temperature, even if this is leading to lattice vibrations which are quantum mechanically called as phonons, quantized lattice vibration. Even if these phonons are created which cause scattering of electrons, and that leads to an increase in resistance. Since it is already supersaturated, so a temperature rise in this case will not have any huge effect. Already तो जितना हो सकता है डिफेक्ट जनरेशन हो ही गया. The further addition of temperature will not cause any problem. That is why this R remains stable. That is why its TCR is quite low. Achha, what about the other one? The one material that we are using is constantan. So this is basically the alpha FCC phase. इसके बारे में लोगों ने बात किया था. So this is also quite stable, and this the karma phase, which is also quite stable. इस alloy के stable होने के पीछे जो कारण है, that is formation of state which is called a K state. Since there यहाँ पे दो ही elements थे, since there are different types of elements, or each element has got its own atomic radii, so there will be total chaos, and within that chaos there will be something called short range order. Explain it. So we are talking about the karma. It is consisting of nickel, chromium, aluminum, nickel is 74% is nickel. Chromium is 20% and remaining 3 carbon. तो यहाँ पे क्या है कि the atomic radii है, basically the resistivity of a material ये डिपेंड करता है resistivity occurring due to the temperature and resistivity occurring due to the defects. So if there is increase in temperature, that will enhance the resistivity, and if there are a lot of defects also, they will also enhance the resistivity. तो इसको हम लोग बोलते हैं मैट हाई सेंसिटिविटी. So in the case of this alloy, you can see that there are various number of elements और सबका the atomic radii ये बहुत वेरी कर रहे हैं. बहुत सारे atomic radii, okay, various range is very huge. So this, due to this, you are getting a total chaos. And within that chaos, you are forming SRO. SRO stands for short range. तो बोलने का मतलब है कि डिफेक्ट्स, ड्यू टू द डिफेक्ट्स, दिस रोडी has increased so much the resistivity to the defect is huge. इसलिए रो को हम लोग इक्विवेलेंट टू हम लोग बोल सकते हैं रो डी. That means temperature increase का इसके ऊपर बहुत ज़्यादा इफेक्ट नहीं है. It implies that temperature rise will have negligible effect. On R. So having a temperature rise having negligible effect on R, इसको हम लोग शॉर्ट फॉर्म में बोलते हैं टेम्परेचर कोफिशिएंट ऑफ रेजिस्टेंस. So this is quite low in the case of कर्माला, as it is in the case of दोनों के केस में कारण अलग है. कर्माला के केस में because of this chaos, because of large number of elements and having different radii is causing increased defect. And लेकिन इस केस में ये कॉन्सेंट्रेट के केस में है कि they are forming a complete solute solution. So both of these alloys, one is the concentrated and another one is karma, are used in metallic strain gauges where we are detecting the strain. Okay. So let us go to the first slide that we started. Our main objective is to sense strain in any system. So we can do it by using a metallic strain gauge that we have recently discussed, just now discussed. And there is one more way, we can use a ceramic or a polymer based strain gauge. Okay. So the ceramic and the polymer based strain gauge uses the property of piezoelectricity. That is, if you provide some sort of strain, it creates a. To understand this, before going into that, you need to understand the classification of the different dielectric materials. इसके बाद तो कुछ क्लास नहीं है ना? मुझे पता है, उसका टाइम टेबल देख के आया. You don't have any class after this, right? So, there's a problem if you want to go, you can leave. हाँ, ठीक है. Whoever wants to go, they can leave. I'm in there. इसका 4 पीरियड्स है इस कोर्स का. That means 60 classes. 60 तो मेरे कितना होगा? 60 मतलब if you go by the rule, it should be 3 क्रेडिट का कोर्स है तो 45 क्लासेस, और अगर 4 क्रेडिट का कोर्स 60 तो होगा नहीं. लेट मी ट्राई. ये इतना इसका वास्ट टॉपिक है ना, कभी करना एक्चुअली इसको बाउंड्री नहीं है. एक टॉपिक कुछ समझाने जाओगे तो दूसरा भी आएगा. ठीक है, जैसे फेज डायग्राम ये सेंसर में तो आ जाता है, यू नीड टू एक्सप्लेन इट. अच्छा, नाउ टॉक अबाउट द you have heard about this dielectric. सुना है dielectric word. Dielectric मतलब die means two. So basically, those which are insulators. They are called basically, उनका एक और नाम है dielectric. जैसे कंडक्टर का क्या नाम है? इलेक्ट्रिकल कंडक्टर. When we say conductors, we are basically talking about metals and alloys. इसका basically हम लोग मीन कर रहे हैं metals. किस तरह का बॉन्डिंग है मेटल्स में? मेटालिक बॉन्डिंग, फ्री sea of electrons moving freely. So insulators are basically ceramic materials. Basically, maybe polymer also, but हम लोग आगे चलते हैं कि ceramic. ठीक है. Give an example of a ceramic material. ceramic material कैसे बनता है? Basically carbides, nitrides, oxides, sulfides. So a metal and a non-metal compound is ceramic material. So there will be a metallic part, and it can be oxides, nitrides, sulfides, so it insulates, but it is not allowing electricity to pass through it. This is the cup, चाय पीने के लिए जो कप यूज करते हैं, वो बेसिकली सेरामिक मटेरियल का होता है, बिकॉज इट इज इंसुलेटिंग टू इंसुलेशन हम लोग यूज करते हैं. इंसुलेशन that is basically made of polymer or ceramic, that is not contact against. So if it is an insulator and if it is a ceramic, we are also calling it as a dielectric, but there are two different types of dielectrics. इसका मतलब है कि if this insulator is exposed to an electric field, ठीक है, no electric field has been applied. Electric field has been applied. ठीक है, ये समझ में आ रहा है? इसमें इसके जो पॉजिटिव एंड नेगेटिव चार्जेस हैं ये रैंडमली डिस्ट्रीब्यूटेड है. When no electric field is applied, इलेक्ट्रिक फील्ड अप्लाई करने के बाद क्या होता है? They polarize. Separate. So there is a polarization taking place. This is called polarization. पोलराइजेशन को हम लोग कैसे डिफाइन करते हैं? डिफाइन करते हैं बाय अ वेक्टर. स्ट्रेन इलास्टिक मतलब स्ट्रेनिंग है. दिस इज इलेक्ट्रिक फील्ड. ये सेंसर में एक बहुत बड़ा प्रॉब्लम जो हम फेस करोगे कि सेम सिंबल्स अलग अलग केसेस में यूज होता है. जस्ट कीप इन माइंड. सो बाय दिस इक्वेशन व्हाट आई एम, दिस इज द डिस्प्लेसमेंट वेक्टर, पोलराइजेशन वेक्टर, डिस्प्लेसमेंट वेक्टर. दिस इज कॉल्ड permittivity. This is the electric field. This is displacement. So since it is dividing into two different parts, positive and negative, that is why this word dielectric is there. Separation into two parts, die. That is why all insulators normally are also called dielectric. Abhi, there are certain classifications of dielectric. What are those classifications? पहला classification तुम लोगों ने सुना होगा. It's called FE. FE. First, let me write the symbols. P, Z, E. P, Y, E. P, Z, R. P, Z, E is okay, start with F. ferroelectric. Like ferromagnetic, this is there is something called ferroelectric. PZE is piezoelectric. Piezoelectric. PYE is thermoelectric. ठीक है, and PZR, this is piezo resistive. फेरोमैग्नेटिक मशीन में क्या होता है, द मैग्नेटिक डोमेन्स पे परमानेंटली अलाइंड, ठीक है। उसी तरह से इफ द पोलराइजेशन इज परमानेंट, इज एग्जिस्टिंग, दैट्स जॉइंट एनालॉजी। हम लोग जानते हैं, हैव यू ऊपर वाला जो डायग्राम है, दैट इज विथ रिस्पेक्ट टू H is the magnetic field, and नीचे वाला जो डायग्राम है, दैट इज विथ रिस्पेक्ट टू E. E stands for electric field, ठीक है। तो यहाँ पे if I am applying some sort of electric field, this I am getting something called a polarization. So if I plot P versus E, I will get a plot like this. ठीक है, and if it is a this stands for ferroelectric material, Fe, and if it is a ferromagnetic material, सेम शॉट, यहाँ पे M. So P is polarization, M is magnetization. This is ferroelectric and this is ferromagnetic. So we are talking about such class of materials where already there is polarization existing in that material. Those are called ferroelectric. Similar to the case of ferromagnetic. मैग्नेटिक डोमेन्स होते हैं ना, तो प्लस टू में पढ़ा है। मैग्नेटिक मटेरियल में क्या होता है, जैसे कि डोमेन्स होते हैं, ठीक है। तो when you are applying magnetic field, all of them get aligned in a particular direction. So that is ferromagnetic field. Already existing जो मैग्नेट जो बनता है, मैग्नेट मतलब क्या है, ऑलरेडी अलाइंड है। सो So those are called ferromagnetic material. Similarly, the electric polarization अगर aligned है domains, तो मैं इसको as a ferroelectric material कर सकता हूँ. FE-RAM आजकल चल रहा है, ferroelectric random access. So this is one class of ferroelectric material. But today we are more concerned with this class of material called piezoelectric material. What is a piezoelectric material? There is, we're talking about strain tensor. So there is strain. Okay, there is generation of polarization. D, the D charge density. This is also called. Charge density. Let's click down. Di has got a certain direction. Strain, तो stress वैसे. Strain से, stress से, strain डेवलप हो रहा है. अभी stress से charge ऐसे डेवलप हो रहा है. On application of force on particular area, मैं देख रहा हूँ कि material में charge चलेगा. So this is a property which is called a charge density. और एक इसका उल्टा इफेक्ट भी होता है. उल्टा इफेक्ट क्या होगा? मैं अगर मैकेनिकल फोर्स नहीं देके, मैं अगर इलेक्ट्रिक फील्ड देता हूँ, ये एक ही इसको एक ही डायरेक्शन है. मैं इलेक्ट्रिक फील्ड दे रहा हूँ नीचे, ठीक है. Then उसमें generation of something called compliance. Forgetting that exactly what there is epsilon. This is what is this? This is strain. So this is the direct effect. यहाँ से क्या हो रहा है? मैकेनिकली मैं स्ट्रेन दे रहा हूँ, उससे चार्ज डेंसिटी हो रहा है, पहला वाला. सेकंड वाला क्या हो रहा है? इलेक्ट्रिक फील्ड दे रहा हूँ, उससे स्ट्रेन. तो इसको मैं I can write it in an equation. I can write di. Okay, let's see. Di is equal to something into sigma j. ठीक है. और दूसरा है स्ट्रेन is equal to Eg. एक में electric field is creating strain and one strain is causing some charge. The interesting thing is what will go inside as a constant. This is Dij Dij is called a piezo electric constant. It's constant. Tensor point. So basically, normal calculations. So it's a हम लोग basically ये we take basically D33 x I j k. So 3 लेने का मतलब है basically 3 is the nothing but the z axis. इसका मतलब मैं अगर z एक्सिस पे मैंने इलेक्ट्रिक फील्ड अप्लाई किया है तो मेरा स्ट्रेन भी z एक्सिस पे है और मैंने इलेक्ट्रिक मैकेनिकल फोर्स मैंने अगर z एक्सिस पे अप्लाई किया है तो आई एम आल्सो गेटिंग द वोल्टेज इलेक्ट्रिक फील्ड जनरेटेड इन दिस एक्सिस. दिस इज व्हाट दिस 333 मींस. ठीक है. इसका जो यूनिट होता है इट इज कम्स इन यूनिट ऑफ कूलम्ब पर Newton. If you look into the first equation, and this is charge density, charge is coulomb. Charge density, मतलब area को they have cancelled out the area, and sigma is the stress force Newton per meter square. This is cancelled हो गया. It's coulomb per Newton in the first case. Second case में क्या हो सकता है? Basically, it's pico coulomb. बहुत कम क्वांटिटी होता है. Pico is 10 to the power minus 12. इस रेंज में कोएफिशिएंट होता है. So let us first see what are the materials which show this piezoelectricity. Have you heard about this? Have you heard this term? ये तूने सुना है इस term को perovskite. Perovskite is a compound. Basically compound जिसका कि जनरल फॉर्मूला है A एक रशियन साइंटिस्ट Perovsky, there is a Russian scientist whose name was Perovsky. He actually invented a compound CaTiO3. So the class of compounds which are having a general formula ABX3, they are called perovskites. So you will have got an X part. What is X? This X can be this X. It can be an oxygen. And it can be an halide. So the piezoelectric materials are basically perovskites, apart from few others. It's a BaTiO3. barium bentonite. This is a perovskite material which is also piezoelectric. We have a material called PZT. PZT stands for lead, zirconate, titanate. So it is basically lead, Eb, Zr, Ti, O3. So it is written in this form, PZT. So all these materials, they are called perovskite and they are piezoelectric. Okay, so I will stop here and I will continue with my